Hi, and welcome to another algorithmic modeling challenge where we're going to model this structure that you see here, which is called the Umbracal, and it's a building by Calatrava on top of the city of the arts and the sciences in Barcelona. I was just informed by people on the chat that this building was on season 3 of Westworld, the TV show, which I haven't watched yet. I stopped at season 2 for multiple reasons. So, but it's going to be an interesting exercise to look at this building, just because we're going to implement like a lot of like very basic form generation. We're going to do some special manipulation of curves and subdivisions of curves, and a little bit of data tree manipulations and list manipulations as well. So it's going to be an interesting challenge, I think. We're going to end up with quite some spaghetti, but I hope it's going to be just tedious but not complicated to understand. Okay, so let's get to it. Well, to start with, we can probably take a look at the shape of the building, which is a pretty good thing to do at the start if you wanna, whenever you wanna start modeling some shape. And we can see that in general, the building is composed. It's basically a canopy. It has like some structural shape. This curve, I believe, is probably very close to a catenary curve because since it's only holding its own weight, then it probably makes sense to approximate that to a catenary shape. You can see that the full thing is basically modules. So if we consider this whole thing one span, one module, we can see that each module has two of these catenary arches. And then in the middle, it has one where the beginning, the ends of the curve do not reach the ground, and where the top of this curve is a bit higher than the average. We can probably see this if we find a better frontal image here. Yes, so you can see that the arches that are in the middle of each span reach a little higher, or you can see that here as well. And yeah, and it's very clear to see here on this image as well. So what we're going to do is, in this exercise, we're going to model those arches. We're going to model each span. We're going to model the arch in the middle. We're going to model all these ribs. We're going to model all these ribs that are joining the span, and we're going to model the profile of this beam as well. And something that is interesting is that the profile of this beam has a height, has a shape, has a depth here that is larger than the depth here. So as the beam goes up, it becomes thinner and thinner, which I guess makes sense because it's probably structurally it has less stresses here on the top than in the bottom. So that's something that we also want to model in our exercise. So how about we go to the whiteboard and do some sketching about what are the parameters that we want to control here, and then we start implementing this. Okay, folks, I saved you the hassle of the 15 minutes that it took me to draw this really terrible sketch. But I would like to remind you that this is extremely good practice. You should always draw a sketch and think about what the variables and what is that you want to control whenever you model something parametrically, because it will help you very much in the process. Okay, so what you're seeing here, what you're seeing here is that I have modeled the basic structure of the building. It's called the Umbracal. I don't know how to pronounce that. That's Valencian. What you can see is that basically we're going to do a modular approach where we're going to have one span, which is what I have drawn here. And the span is going to be two curves that are going to have a width and a height that are going to be controlled by 3 points. And then it's going to have another curve in the middle, which is also going to be driven by 3 points. But those 3 points are going to be elevated from the ground on the base by the factor of h1. And the point on the top is going to be a little higher than the point on the neighbor curves, a little higher by a value of h2. Okay. Once also the width of the span in that direction is going to be called d, as in depth. And at the same time, we will also want to control how many spans of this module we are replicating in the x direction. You see the coordinate system that I drew down there. I can't up. I can't down there, exactly. So we want to control how many of these, and we want to control how many ribs. So how many of these partitions are going to be present in the in each one of the modules. Because at the end of the day, what this is about is we want to do algorithmic modeling. We want to model something that is entirely controlled by parameters as much as possible. So that's why instead of assigning numbers, we assign variables or parameters, so that when we are done, we can change those numbers and then we can adapt the shape of the building, and we can decide what is the final shape that we want to get. Okay, that is the beauty of parametric modeling. So let's get started. Wonderful. So what I've done is I've spent a little bit of time preparing my definition and coming from all those parameters that I have defined in my sketch. I have mirrored those with Grasshopper sliders. So I have the width, the height, the depth. I have h1, h2, number of ribs, etc., etc. And the only thing that I have added is that I have created a physical point here in Rhino that I have brought as a parameter in Grasshopper, because what I would like to do is I would like to able to, once I have finished making this whole thing, I would like to be able to change the point where this thing starts and basically be able to place this building anywhere on my window, on my Rhino window. That would be really cool. So that's why I'm going to start with this point, which is going to be my starting, basically the origin of the building, and I'm going to base the location of all the other points as a reference to this one. Okay. So what are the first thing that I'm going to do? I'm going to create the 3 points that define the first arch. Okay, and that's going to be super easy, because what I'm going to do is I'm going to say, well, the first point on the other end, I need to basically take this point and move it by a distance of w in the y direction. So I'm going to create a y vector with the length of w, and then I'm going to move this point by this vector. Okay, that is going to give me a point that is going to be the second point. Is going to be the other end of this point. And now something that I can do is I need to find the point that is right here, and that point is going to be in regard to this one is going to be a distance of half width in the y direction and a full h in the z direction. So I can probably create a vector from x, y, z coordinates. X is going to be 0, y is going to be w divided by 2. So division. I actually don't like doing. You will see this. I actually don't like doing algebra with regular components. I like expression components a lot, because I see them. I can see the expression, and I can. This is perhaps for dividing by 2 is very simple, but when it's a bit more complex, it kind of makes sense, I think. And then height is going to be this, and then I can take and I can move all of this, and I can copy paste this, and I can move the origin point by this new vector. Okay, and if I take a copy, I like doing this a lot too. If I take a copy of this point here, right, and I place it here, so I have those 3 points here, and what I can do now is I can just draw a simple interpolated curve between the first point, the one in the base, the second point, which is the one on the top here, and then the third point, which is the one on the other end, giving me this curve, this shape, which is a NURBS curve. One thing that I would like to say about this is that I believe in the original building, this shape is probably closer to a catenary. I believe, I'm not entirely sure. And Grasshopper does have catenary implementations, so you can use a catenary curve. The only thing is that the catenary curve in Grasshopper is controlled by the 2 base points, but it's not controlled by a height. It's controlled by the full length of the catenary. So it's a little more cumbersome to define, like, the length of the. You don't know exactly where the height of the catenary is going to end up. So it needs a little bit more of background. It's a bit less intuitive, but also at the same time, I will want to mirror this exercise in purely C#, and Rhino Common does not have a catenary implementation, so I will not be able to do the exact same process. Perhaps we can do a geometry gem where we discuss catenaries at some point, maybe in the future, but for the time being, I'm just going to use a simple interpolated curve. Okay, good. So I'm going to group this because I like being very tidy and very clean. So this is the first curve of my span. Okay, and I'm going to add this to the group. What is the second thing that I would like to do? I would like to copy this curve and have like a second curve that is moved in this direction by a distance of d. Okay, as you see in the diagram. So what I'm going to do is I'm going to create another from d. I'm going to create a vector in the x direction, and I'm going to move this curve. I'm going to move this curve by this x vector so that I have the other curve on the span. And this is going to be a little like this, or this is going to be more like this to look closer to the original building. I don't even know what I'm doing. Okay, and now I have the other curve of my span. Okay, and I can probably start turning off the visualization of these points by I'm hitting Ctrl Q so that I stop the visualization of those points. And the beautiful thing about this is that I can now move this original point anywhere, and you can see how the building is just moving around with me. Okay, what is it going to be next? We're going to draw the curve that is in the middle of the two spans curves. Great. Let's take a look back at the diagram. So to draw the curve that is in between the two spans, I would like to start with the point that I cannot point to, the point at the base, which is going to be a point that is going to be in between the 2 points that form the curves of the span, and it's going to be elevated by a distance of h1. Okay, so that's going to be also fairly easy to do. I'm going to keep using vectors because I like vectors a lot. So this vector is going to be a vector that is going to have in the x coordinate is going to have a distance of half d, and then in the y coordinate is going to have a distance of h1, which is a parameter here. So I'm going to copy this and I'm going to do half d, and that's going to be the x coordinate, and for the y coordinate is going to have nothing. It's going to be in the same plane, so I'm going to disconnect this. And for c, what we want is h. Okay, so that's going to be, and we're going to take the point, we're going to take the original point here, the base point, and we're going to move it by this vector here. And you can see that it's all the way up there because h1 has a really high value right now, but you can see right now it's right in the middle, okay, of those 2 points. I like that. So that looks good. And then I'm probably going to move this point a distance of w so that we have the other end. And I've done that before, a distance of w, so I'm going to copy paste these two. And because I have this point already, I now have the other point. Okay, so yep, so now I have the other point on the other end, and now I need the third point, which is going to be this one here. Okay, what can I do about this one? What I can do is, if you remember, I have this one here, and what we said is that according to our diagram, what we said is that that point here is going to be on the same plane as these two, but it's going to be elevated at a height of h2. So if we do that, then I can say I'm going to take this point and I'm going to create a vector that is going to be half d, which I already have here, and then so I'm going to create a vector that is going to be half d, which I already have here, and c is going to be h2. h2 is going to have a value of like something very small, and then I'm going to use move, and I'm going to take the point, this point. I'm going to move this point by this vector that I just created here. Okay, so I have starting point, end point, and middle point. So I think we're pretty good to go. So I'm going to, what am I going to do? I'm going to create an interpolated curve between these 3 points. So this one, between this one is going to be the first one, this one is going to be the second one, and this one will be the third one. Okay, and I'm going to turn the visualization off and visualization off, and this is going to be the curve that is going to define the middle, the center of this span. Okay. All right. So is this parametric enough? Let's see. This is a check that is very useful to do. Let's see if we move the parameters that do things move around in a way that makes sense. So width, everything is changing accordingly. The height, it looks like things are changing accordingly. The depth, it changes. Things are moving. Nothing is going off. This goes up. This is going up. So it looks like things are pretty tight. So I like what I'm seeing here. So I think we are now at a very good point to move on to the next step, which is going to be what? Which is probably going to be figuring out the ribs. Okay, so let's take a look at that. This part is going to be super easy. The only thing that we need to do now in order to create the ribs is to take the starting curve and then the middle curve, divide each one of those curves in the same amount of points, and then just join those points with straight lines, okay? And then for the other end, we can do the same with the two curves, or we can just mirror the initial points, okay? We will have to take a look at this particular situation where of the offset, where the ribs don't start at the very beginning of the curve, but we can take a look at that in a second, okay? So pretty easy. We're going to go to the first curve, and I'm going to subdivide this curve, divide curve in a bunch of points. So as I plug this in here, this is by default using 10 as the number of segments, but I probably want to connect this to the parameter that I specified, the number of ribs, which I'm going to set at something a bit more reasonable. Let's say 44, I don't know. Does that sound reasonable to you? Yeah, why not? I like prime numbers a little bit better, but whatever. And then we're going to take, and we're going to copy this for the curve in the middle, in the center, and we're going to subdivide that curve by the same amount of points, okay? So this is very important, because otherwise there's going to be some kind of conflict, okay? And then, very easy now, we can just join these points and these points here, and then create all these ribs. Because we have joined them by the same amount, if we look from the right, you can see that the center, the one in the center, is perfectly vertical, which I believe is how it works also in the original building. Okay, so that's great. However, we have a little bit of a problem, and the problem is that, as we said, I don't want the ribs to start right here at the beginning of this curve. I want some kind of offset, so that the ribs start like a little bit farther up. In order to do that, I cannot work exactly with the original curve. What I would like to do is I would like to take that curve and kind of, if you will, kind of shrink it, or maybe take from this curve, take a subset of this curve that starts somewhere a bit higher and somewhere and ends a little higher. Okay, how can I do that? I believe we can do that by creating a new curve from a subdomain of the original curve. What does that mean? It means, if you've seen some of my other tutorials, I just want to remind you that NURBS curves have this thing called the domain. So for example, if I say domain and I pass the curve here, you can see that this is telling me that this curve has a domain that goes from 0 to 12.33. That doesn't mean that the curve is 12 meters long. it means that the curve has an internal distribution of the parameter that goes from 0 to 12 point something something. And if you want to know more about that, you can check my other lectures. So I think what I would like to do is I would like to find a component that, given a curve, it gives me a new curve from a subdomain of that. So let me look that up and see if I can find something that can do that. Okay, I didn't really find a component that gave me a subset of the curve with a smaller domain, but I found an alternative method, which I'm going to explain right now. And it is due to the fact that what I really want to control is the vertical height. Is the vertical height at which this point, so this point here, would start and where the ribs would start. And what I can do is I can divide this original curve, so I can divide this curve, and I can split it at points that I can compute myself. But what I need to know first is what is the parameters, what is the t along this curve that I want to split the curve at. And I think that a good method to do that could be to create a horizontal plane here, then cut this curve, cut the original curve, the first one, along this plane to find the 2 points where the offset is already set and where we would start the ribs. And then if we find the parameter at which that plane cuts the curve, then we can probably split the curve at those parameters and then use the subset of that curve. Let me explain. This is sometimes much harder to explain than to just do it. So let me start by creating a horizontal plane, okay? And I'm going to move this farther down the road. Let me create a horizontal plane that I'm going to move in the z direction by a factor of offset. So I already created here a variable called offset, and I'm going to move this all the way up. So I'm going to move my plane a little bit vertically, you see? So this is the cutting plane that I'm going to use to trim this curve. And let me turn all of this off. So now I'm going to use a mathematical intersection, and I'm going to compute the intersection between a curve and this plane, the curve being the original curve here, and then the plane, the one that I have just created here. All right, you see, I have now gotten these 2 points on the curve that are at a vertical distance offset from the base plane. And the beauty of this component is that not only does it give me the actual points, but it also gives me the parameters at the curve at which the intersection is happening. So think of this as relative to the domain of the curve. So if you remember, curves have domain, and the domain of the curve here is from 0 to 1233. So you can see that these points are cutting the curve at domain 0, 59, which makes sense, it's like close to the beginning, and 11.74, which also makes sense, which is kind of close to the end. All right, so this is looking great. So I think now I can take a division and I can take a shatter component that is going to take the curve and is going to take the 2 parameters and is going to divide the curve now in 3 segments, in 3 planar curves. This first chunk, the full middle chunk, and the last ending chunk. But since I'm only interested in the one in the middle, I can use a list item component to fetch from this list, to fetch just the second element, which is the one that has index number 1. If I do that, you guys can see that I only have one planar curve, and if I hit here, you can see that highlighted is this curve that is exactly just a subset of the original one trimmed by these 2 points. Some folks in the chat suggested that maybe I could take these 2 points and then the original point on the top and then create an interpolated curve between those three as opposed to this shatter. And that could have been a workaround. It's just that I would not be guaranteed that the interpolated curve would be exactly the same. I believe, I'm not really sure. So I think just for the sake of purity or cleanness or elegance, I think this method is a bit more elegant because it really just gives me the original curve for sure, but a subset, a smaller subset of it. Okay, and then just as I calculated this part here, I can now use this subset of the curve and plug that into the subdivide and create the ribs from this part, from with this offset, which if I make much larger, you can see that it's working great. So I like that a lot. And okay, and then I guess that for the other, so this would be the ribs on one side, and I guess for the ribs on the other side, what I can do is I can just probably, because the domains of the two curves are probably going to be the same, I can probably just take the other curve, no, not this one here, and cut it like that. Okay, and then just copy paste all of this here. So what I've done is for the other curve, I didn't need to compute the intersection anymore because I'm assuming that since they are clones, the domain is going to be the same, so I can shatter directly on these two parameters and get that subset curve. So I can do now is I can plug that in here, and then I can get the ribs that are on that other side. Okay. All right, this is looking good to me. Let's move the parameters around a little bit to see if things work. This looks like it works. This works. This works. Everything is working. I think everything is very tight and very solid. So I think we're on a good spot to continue with this. So let's move on to the next step. I believe the next thing that we're going to do is we're going to implement the beams. And for that, I would like to be a little faithful to the original building, where we can see that the section of the arch is much larger at the base and is much thinner at the top of the beam. So I have drawn this diagram here, which of course is terrible, but the takeaway of this diagram is that we're going to create a shape that is going to be much wider near the base and is going to be very thin at the very top. And we will want to control the shape of this section in two ways. We will want to have a value for the height of the section at the base, so that's going to be D1. We would like to have a value for the section at the very top, that's going to be D2. And then we would like to implement an algorithm that, as we are moving along the arch, the section decreases based on how high up I'm gonna say that based on how high up the section is. Okay. Another thing that I would like to probably have here is going to be the width of the section. That's going to be small w. Okay. And so for that, what we're going to do is first we're going to start by doing a section that is constant. So we're going to start with W and D1 for the whole arch, and then we will perform some changes so that the section decreases with the height of the arch. Okay, let's go back to drawing. So where is my mouse? Where is my mouse? Ah, here. Okay, so we have all of this, and that's great. So we have the curve, and this curve is the curve that I want to use. So I'm going to move things a bit here outside of the clutter. Okay, and what I would like to do first is I'm going to set some parameters here. I'm going to create them here, and then I will move them back to the origin. So this one is going to be D1, then this is going to be D2, and then this is probably going to be small w. Okay, and then I'm going to take this curve and I'm going to subdivide this curve in a bunch of perpendicular frames. So you can see that here I am subdividing in a ton of perpendicular frames. How many? I'm not really sure. I'm not sure how important this is. I think it would be important that the number is even, because we would want one at the very center of the arch. So maybe we choose here to have like a fixed value that is always going to be something like, for example, 30. Or maybe we could plug in a slider here. I don't have a strong opinion here anyway, so I'm just going to leave it there. And I'm going to make the preview of these planes a little smaller so that it's not clogging our view so much. Okay, so now what I'm going to do is I'm going to place on top of these planes, I'm going to draw some rectangles. Those rectangles are going to be defining the section as we move over the arch, which we will then loft with a surface so that we get a continuous solid geometry. But you can see that all these arches are defined by the x-size in x and y, and they are defined with domains. Okay, so what does that mean? It means that if we want this bottom section here to be of the size w in this direction, we would need to say that the size of the rectangle is a domain that goes from minus half w to positive half w, because we want this section to be centered on the axis of the arch. And then for the height, we would want the height in that direction to be a domain that goes from minus half d1 to plus half d1. So let's implement that. So we have d2, well, not d2, we have d1, and we have the width. So I'm going to create a domain that is going to be, I'm going to create, this is going to be 0.5x, and so that's going to be d, and I'm going to create also something that is going to be minus 0.5x, and I'm going to construct a domain with these two values. Okay, so this and this, and you can see that my domain now goes from it's the other way around. From minus to positive. Okay, and if I plug that into the x, then we have this, and then, but if I do the same with w, and I plug that into the y, you can see that now if I hide the planes, and if I hide everything else, I'm going to hide all these bars here, you can see that I have these rectangles that are growing, that are perpendicular to my arch, and that have like a d direction and a width direction, and are going all the way up. Okay, so that is looking good to me, and I think just for the sake of showcasing, I think what I'm going to use here is I'm going to use a sweep one, which is a surface generation method that takes a rail curve. So there's a line, there's a curve that defines the main direction of the surface, and there's a list of section curves that are defining the section of that surface as it moves through the rail. So I think the rail is going to be the curve, and then the sections are going to be all these rectangles that I just created. And you can see that I now have this beam that the direction of the beam is respecting the axis of the arch, and each one of these rectangles is the section of this beam at that point. So this is looking good to me. But now we need to figure out a way to make the size, so the size of the height of the depth of the section, to be variable according to a height rule. Okay, so let's take a look at that. Okay, great. The way we're going to do this is by implementing a very, very simple numerical rule, where we have two sections here. One has a height of D1, the other one is height D2. And what we need is, based on how high or how far from the ground each one of the sections is, we need to reduce incrementally between D1 and D2. Okay, I'm actually going to do this example with numbers. So let's say I'm going to create a new layer here. I'm going to draw some numbers here. Let's imagine that the section that we have here is, for example, 75 centimeters. And the section that we have here is 50 centimeters. And we have 1, 2, 3, 4, and 5 sections in the middle. Okay? It's kind of easy to see that this one should have 70, this one should be 65, this one should be 60, this one should be 55, and the other one should be 50. Okay? But how can we find a numerical rule to do that? Well, if we know that the difference between these two sections is 25, so 75 minus 50, if we know that the difference in the depth of the section is 25, what we can do is we can compute a rule where we say how far off from 0 to 1 is this point from the base. So if this is 1, we can say that, because it's 5, we can say that this point is 0.20 away from the bottom. This one is 0.40 from the bottom. This one is 0.6, 0.8, and this one, the top, is a full 1.0 away. This is called a normalized distance. We're not measuring the real distance, we're measuring the proportional distance between the two ends. And then if we take and we multiply the proportional distance by the actual difference in those two sections, so this 25 multiplied by 0.2 gives us 5, so we can subtract 75 minus 5 is 70. If we multiply 25 times 0.4 is going to give us 10, so 75 minus 10 is going to give us 65. And then, so basically, if we multiply the normalized distance by the difference that we want between the two sections, that's going to give us how much do we need to subtract from the main section height to get the proportional section height at that interval. Was that clear? I'm not sure about this. Sometimes I see these things clearly, but I don't know if I explain this in a way that makes sense. Let me show the implementation and then we can judge. So we have the base at the point at the base, which was this one here. Okay, so I'm going to take this point at the base, I'm going to bring it all the way to where I'm working, and I'm going to take the other point that was, what was it? It was the point at the top, it was this one. So I'm going to take that point at the top here. Those are the 2 points, my 2 reference points. Okay? Point on the bottom, point on the top. This one I'm going to deconstruct so that I can find the z property of each one of them. Okay? And so that I can find this z property of each one of them. And actually, I don't really need the one in the top. Sorry. Now, I have D1 and D2. I can subtract one from the other. So D1 is going to be bigger than D2. So D1 minus D2, this gives me the difference in section depth. Okay? And now what I can do is I have all these frames that I have created, all those planes. Each one of those has an origin point. So if I can deconstruct the plane into each one of its components, you see that it gives me a lot of points, and that it gives me the x, y, z vectors of those points. So if I deconstruct the origin, I can see that here I can get the z coordinate I can get the z coordinate of each one of those points. All right. Okay. And if I now subtract the height of each one of those points minus the height of the base point, you can see that this is how far off each one of these points is vertically from the one in the bottom. But this is the Euclidean distance. What I want is a proportion. I want to know if these points are from a scale from 0 to 1, how far off each one of them is. Okay, and and for this, for example, I can take the maximum of all these points, or no, I can actually take the point that I deleted. I take this point here. I take, where is this point? No, not this one. I take this point here. Yes, I'm going to bring that point, the point on the top. I'm going to find its height. Okay. And then I'm going to divide each one of these heights by the height of this point. And you can see that now what I get is a nice list of relative heights. So this point is proportionally is like 0 distance from the base. This one is 0 point something, 0 point something, and it goes increasing all the way until 1, which is the point at the top. The point at the top proportionally is the farthest away in the vertical z height from here. Now, I know what the large section is, so this is D1. I know what the smaller one is. I know what their difference is. So if I multiply this proportionally, the proportion from 0 to 1, with the difference in sections, you can see that I get a list of how much do I have to subtract from each one of the sections. So from the section in the base, I have to subtract absolutely nothing. And then I have to start subtracting a bit more all the way to the center, in which I have to subtract the full 0.48. Let me make this a bit more round numbers. So if the section at the base is 70 and the one at the top is 20, you can see the difference is 0.5. And you can see that now I have created a list of how much the section gets reduced as it goes up on the arch. So now it's just as easy as saying for each one of these sections, so take D and now subtract from D, from the value of D, each one of these increasingly diminishing sections, and then plug this value to where we are calculating the heights of the section. You see that? And then you can see that now each one of the rectangles has a different depth, and that depth is proportional to how far off they are from the bottom. Okay? This was a little convoluted to explain. I hope I did a good job at that. But let's see if this actually works. So if I change the base, you see that now it's much thinner. Now it's very thick. This is actually quite cool. Actually, very thick. This one increases. Now it's very, very thin. Okay, the width is constant. That doesn't change. Okay, and then if I mess up with the height of the whole thing, you can see that we still get the nice proportional effect because everything is parametric. It doesn't really matter how high this is in Euclidean space. What matters is the difference between this point and this point, and that is how things are computed here then. Okay, that was cool. Let me shrink this a little bit. I don't like it's looking too fat. It's looking too wide, and this okay, I like this a little better. Okay, and so this was for that one, and I'm going to group things a little bit here to make things cleaner, and I'm going to leave this here because I will want to move it at the beginning, where all my parameters are. And I think we can probably apply this to maybe this. We can apply the same logic to the curve in the middle, or maybe we should use two other different parameters. I'm not sure. So I'm just going to do a different one because yeah. So I'm going to copy all of this and paste it here. I'm going to give this different names. So this is going to be the one in the middle. This is going to be the one in the middle. This is going to be the one in the middle. Okay, and I'm going to reduce this. So that's going to be 0.6. This is going to be 0.1, and this is going to be because this is not really carrying much stresses. But the curve that I'm going to plug in here is going to be the one in the middle. The one in the middle, but the points that I need to plug in are different. This has to be the point at the base, which point was that? It was this point here, and for this one, this was the middle point, so that was going to be that's going to be this one. But we could have actually done this a bit more programmatic, and instead of relying in the previous points, we could have just take the start point of the curve and the middle point of the curve, and make things a bit cleaner. But yeah. Okay, so I'm gonna clean this up a little bit, and okay, and so now it looks like we have the profile curves. Okay, so what is our next step? And I guess the last thing that we want to do is we have everything ready to go. So we have our ribs, we have our beams, we have the surface for the beams. We could put some pipes here, so we could put some thin pipes here, curve, and the radius is going to be something like something small probably. So that's going to be, the radius is going to be something like 0.01 or 0.03, 0.03, you know. So we can probably just put some pipes in here. Pipe radius. And I guess the only thing that's left is like to take all this geometry and then to replicate it in a matrix going in this direction. So that's going to be super easy to do. So let's take a look at how to do that. I'm going to create the number of spans, okay, and we have these spans. So what I'm going to do is I'm going to create a series of numbers, and I'm going to create a series of vectors with those numbers, which are going to define how many repetitions we do. So I'm going to create a series, and I'm going to the first number is going to be 0, like the number of the step size of each system is going to be 1, and the number is going to be, so here let's say I have 10 spans. So here you can see that we have this many elements, and I probably want the step size to be d, so that what I'm going to create is vectors that move this geometry 1.5, 3, 4.5, 6, etc. in the x direction. So I'm going to create a lot of these. I'm going to create numbers to they increase successively, and then I'm going to use a x vector to create translation vectors. And now with this vector, I can just very easily start taking geometry that I want to replicate and start moving it with all these vectors, creating a matrix. So for example, what is the curve that I want to take? What is the curve that I want to? So this curve. So this is going to be, for example, if I bring this curve, this is the main curve. I want to replicate it like 10 times, for example. Okay, so that's going to be the main curve. Something that I want to replicate 10 times as well is going to be the middle curve, the one in the middle. So for example, where is the one in the middle? The one in the middle is it this one? No, it's this one here. So I'm going to take this, I'm going to plug it in here, and then I'm also going to replicate this 10 times. So we have that. Now I can also bring in all my ribs. So for example, the ribs are, the ribs are here, I think. These are the ribs. And okay, and I'm going to need to do some modifications there. And those are the ribs, yes. And you can see that the ribs are doing something weird, and that something weird is happening because of data. Okay, so you can see that. No, where are the ribs coming in? Yeah, so these are the ribs, and you can see that I have a list with a bunch of elements. But I also, for the translation vectors, I also have a list that has a bunch of elements. So what's happening is that the first one is being moved by the first vector, the second one is being moved by the second vector, the third one by the third vector, the fourth by the fourth vector, and that's why you see the first one here, the second one here, the third one, and one at a time until the very end, which uses the last vector to repeat that. This has a very easy solution, which is to graft the tree, and then to just use the grafted tree there. If you want to know more about why this is the case, you can check my intro to Grasshopper series, where we do data manipulation. And now here we have all the ribs. There you go. And I can also do a similar operation for the B reps. So where are the B reps? So here are this guy here, which is going to become all the way down, and then probably this one I want to replicate it as well, and probably I want to graft this. Okay, and then I can do this with the pipes probably as well. Where are the pipes? Yes, so pipes and pipes. Okay, and then I have everything replicated except that the very last arch is missing. And that's because for the last one, I probably want to use a series where I increase this by 1 unit. So I'm going to keep this for everybody except for the first one. So I'm going to copy in this, but here in how many elements I want, I'm going to create an expression. I don't like creating expressions in components. I like to have this, so maybe I'm just gonna replace this here and then create an expression where I say this is going to be x plus 1, and so I'm going to increase by 1 value, and then so that creates a list of vectors that is 1 unit longer, and then that's the one that I'm going to use so that I have an extra element at the very end. And I'm going to use that one also for the vrep that is coming from here, so this one. So I'm going to copy and paste this, and I'm going to disconnect this one, and for this one I am going to use this other list, the one that has an extra element at the very end. Okay, and I think with that we are in. I'm going to group everything that is curves in one component here so that I can turn them on and off with one go, and I'm going to group everything that are B-reps here with one component as well, so that I can see, I can turn everything on and off just with one component. And I'm going to disable the visualization of everything in the middle. And piece of cake. So now I can turn everything on and off. So you can see that I can only show the B-reps. So I have my very nice building, and I can mess around now with the widths, and I can mess with the heights, and I can mess with the number of ribs, and I don't know. And if I want the surface, because I want to render it for a competition, then I already have this. This is the geometry that I can bake, for example. So I can bake this. But if I don't need this, this is very expensive to compute. So what I can do is I can disable this component so that the whole definition is a bit more lightweight. And what if I want? There you go. And here I still have the curves, which are useful for me to generate, for example, like the axis diagrams or the structural plans would be very helpful to just have the axis lines as opposed to the B-reps. Okay, so so I think with this we're pretty good to go. I hope this was useful, and stay tuned for more algorithmic modeling challenges. Thank you.